A quick video to show you how to answer these rotational conformation analysis questions using the graphing function in SmartWorks. Okay, so just a brief overview here. We're going to use the chart below to draw the conformational analysis graph of ethane according to the Newman projection progression below. Note that we need to round all of our calculated values to the ones place before we enter our data point on the graph. Okay, so you see here we have this progression of different Newman projections. For each one, we're going to use this chart to calculate the energy, and we're going to then plot it on this graph below. Okay, note that the graph, when you start out, already has some data points laid down. This is just to help draw the graph and to give it the correct shape. So do not delete, do not touch these data points here. Okay, what we're going to be doing is laying down data points between that correspond to the energy of the structures above. So this first structure here has all of our hydrogens staggered. There are no methyl-Gauss interactions, so this is the lowest energy structure here, which would be at energy 0. So what I'm going to do is I'm going to lay a data point between these two existing data points down here at 0. That's my energy of my first conformation. Okay, I get up here, now I have my staggered conformation that has 3 HH eclipsed bonds. So each one comes with a penalty of 4 kilojoules per mole. So if I totaled everything up, that would give me 12 kilojoules per mole. So now I'm going to go between my next two data points up here and lay down this data point at 12. Okay, and we're going to continue on. Ethane is a very simple structure here, so each one of these staggered conformations has the same 0 energy, and each one of these eclipsed conformations has the same 12 kilojoule per mole penalty. So my next data point will be back at 0, then now back again at 12, at 0, and then at 12 again, right? So again, I had these existing data points. For each structure above, I calculated the energy, and I laid down that data point between those two. So then I look to the next two, that was that higher energy eclipse structure, etc., etc. Okay, so to put down this graph, we're going to use this tool right here, and this is by far like the clumsiest aspect of this graph drawing tool. You need to actually first go and select that first point that we're going to use to draw. And it's important to start and end with the points that I had already laid down for you. That's how you get the correct shape to your graph. So I'm going to use my bond tool here, or my curve tool. 1, 2, 3. There's my first curve. Okay, going back again, very clumsy, but you have to select, because right now it's selecting that curve, so I have to go back and select just that point, and then 1, 2, 3. Again, select just that point. 1, 2, 3, and keep on going. Whoops. Select just that point. There it is. You can see it gets a little darker when you select it. 1, 2, 3. Oh, and so for that one, for whatever reason, it didn't like it. It was mad at me. So I'm going to have to undo that last one and try again. Okay. Cool. And so that's part of why it's important to round to the ones place for your calculations, is that that's where it allows you to lay down these data points. Whoops. So I selected it, get my curve. And now I've connected from the first data point that was already laid down to the last data point, and I'm done. Okay, so that's how we're going to go about solving or drawing these graphs for this rotational conformation analysis here. There's going to be some existing data points on your graph when you open it. You're going to lay down points in between those existing points corresponding to the energy of these structures, and then connect everything with that curve. Again, when you're drawing the curve, you must first select the first point you're going to use, then the curve drawing tool, and connect 3 of them, right? You're always going to start at one of the existing points, go to one of your new points that you laid down, and then end at one of the existing points. Each curve gives you one side of these parabolas here.